I'm going to have the oldest guy and Amy introduce me. I'm the oldest guy, and Amy, let me introduce me. A few things that are important is I come from a town that you've heard me say before, Melville, Saskatchewan, that has 4,000 people counting dogs and chickens. The reason I say that is that throughout all of the years I've been an academic researcher, I've met a lot of people who forgot where they came from, right? Don't forget where you come from. That's the first thing. The second thing to say is about the talk today is that I was at a conference workshop where another one of my Amy colleagues was talking, and when I spoke, I said, "Let me beg your indulgence. I'm likely to say things that will annoy some of you, but I do it in good spirits, in the spirit of scientific challenge, and hope that you accept the challenge to give me feedback so that I can learn." Then one of my Amy colleagues, after I spoke, got up, Dale Shermans, who many of you know, and he said, "Unlike Randy, I expect I'm going to annoy everyone, not just some of you." And so today, the talk I'm going to give you may annoy some of you, but it's given in a spirit of what I've observed. And almost all of the discussions that I lead today, or all of the presentations I make anywhere around the world, are really targeted to graduate students because after so many years, I think I've supervised more than 80. Osmar and I are neck and neck. I hope to achieve 100 before I retire. But in that experience, it's my job and responsibility to reduce the obvious misconceptions I see people holding, because that's what makes you stronger, what makes our university, our department, and Amy stronger, because the more you know and the better and stronger your perspective is, the better you will represent us in the world. So let me go on. Does everybody see the elephant on my hat? Elephant on my hat comes from a hat that comes from a place I used to visit quite a bit when I lived in Malaysia. Kuala Ganda is the elephant sanctuary, publicly funded to rescue sick, damaged elephants, whether it's PTSD or physical ailments. It's a wonderful place to visit. And this is about an elephant in the room. And so for those of you who have ethnic, cultural, linguistic backgrounds, I'll say a little bit about that. The notion of elephant in the room is described. This one I asked Cloud 3.5 sonnet from Anthropic to describe what it meant. And here's a snippet from Cloud that says, "The elephant in the room seem to, as you can read." And the important part is the phrase describes a situation where everybody pretends not to notice something obvious. That's what the notion of an elephant in the room. So what I intend to convey to you is the idea about whether or not there is a large spectrum of foundation models. So you will find yourself misaligned with me if you think that transformer construction of deep neural networks is the only foundation model on the planet. Not only are you wrong, but it impedes how you learn about what the basic foundations of AI will be. So maybe the subtext there is that don't listen to Sam Altman. That's another. So here's the outline of what I want to do, is that here's one of the deficits I see in many of our graduate students, not all, but many. I see this through the whole spectrum. For example, I teach Compute 272 with Lily Mu, with Mohammed Salavatopour, with Vadim Belitko, with Carrie, and I always forget the hyphenation of the last name, Enmens Depp, or Depp Enmens, Enmens. And in those, I see the full spectrum from undergraduates through PhD students and postdocs who sometimes miss things, and sometimes they miss things because they're too old. Literally, you should rethink anytime you find yourself using the sentence saying, "Oh, but that reference is old. It's from 2019." You should always rethink how you say that. So that's part of what I'll do in this spectrum. Maybe the fundamental questions are to say, what are the foundations of debugging? How to change your perspective on what foundation models are and what debugging means. And then to give you a hypothesis about what I call, some of you are familiar with with the development across information systems. So some of you will claim to be full stack developers. What I'm going to tell you is that there's a different notion of full stack when you talk about foundation models. And I'll give you an hypothesis about how to stack those up. Some of you will see that scalability is another maybe smaller elephant in the room, but it's not clear. So here's what I want to talk about first is the foundations of debugging. When I say debugging, I mean exactly the process you go through all the way from writing a simple Python program that doesn't do what you want. So you have to instrument it within an environment somewhere. So you have another piece of contextual code that allows you to place your not working program in that context and use that program to debug your program by instrumenting it in some way. That's what I mean by debugging. Now replace your Python code with 1 trillion parameter deep neural network. It's the same thing. Is if you want to debug it, if like some LLM providers have done, they've debugged their code and they've debugged their foundation model so that it no longer reports that the current estimate of the population on Pluto is 4 million. So that doesn't happen anymore. The primary questions are, one, they choose to debug it by having people tell them the output is wrong. But two, how do they do that? And that part remains a mystery, but you'll see that. So here's what I claim the mathematical foundations of debugging are. They're about writing formal systems like computer programs to help us debug other computer programs. And the first person to articulate a framework for the challenge of debugging was Kurt Gödel at the University of Vienna many, many years ago. But you can see from a Google Gemini summary is the problem is that the formal systems we have, including all programming languages, they themselves succumb to this fundamental mathematical challenge. You can't change that. You can't ignore it. Engineers do for the most part. But you can't change that fundamental property is that you can't write programs that, as you'll see in the halting problem, can decide whether your program can be debugged or not. That's another way to think about it. So Gödel is worth paying attention to. The first theorem, I think, was 1931. So if it disturbs you that this is an old reference, it disturbs me that you don't understand the foundations of mathematics. Here's another one. This one's much more interesting from an application point of view. So you can find this online. The slide should be available if everybody wants. But one of the lectures that Stephen Hawking gave with his apparatus for speaking and generating sound was called The End of Physics. What he meant by the end of physics is he already knew about Gödel and Turing and the halting problem and the incompleteness theorems, said that the characterization of all of physics in this massive, wide pursuit of formalizations of string theory to be a theory of everything is doomed. And this paper lays out why in a way that even a computer scientist can understand. But it's the same thing. You can read what I've captured here. It's like the system that you use to describe the way the world works is part of the world. An American comedian from the 30s who did a lot of movies then, and his brothers, Groucho Marx, said what amounts to something I say when I talk about anomalies of set theory in Compute 272 is when Groucho Marx was nominated for membership in a comedy hall of fame, he said, "I'm not sure I want to be a member of a club that would have me as a member." That's another way to think about this. And this is easily read. It's only about 5 pages. Now, closer to home for computer scientists, the halting problem described in this paper, famous paper by Turing, you can see that it was received 1936, published in November of that year. And maybe the most interesting thing from this fundamental principle and the halting problem is he noticed how similar it was and how it was related to Gödel, so he knew that. But what he said is computer scientists, when you're engineering a piece of software, if you're aware of where the halting problem boundaries are, you can avoid them. It's like don't getting too close to the edge. Now, all the way back to debugging is the systems and the programs you write to help other people debug their Python programs have to avoid getting too close to the edge. That's one way to think about that. Now, I'm going to before I move to the next segment in my outline, I'm going to show you this. So one of the people I pay attention to is a guy named Gary Marcus, who Dale Sherman said, well, he's only criticizing these LLM models. He hasn't offered any advice about how to improve them. You can think of what I'm doing today is the start of advice about how to improve them. But this was an example that's a year old now. A year ago when I found this from Gary Marcus, I replicated the image from Mid-Journey, and I tried to do it yesterday, but I couldn't because it's behind a paywall now, and I refuse to pay for something I already know how it works. But here's the question. Now, in light of Gödel and Hawking and Turing, with the difficulty, the fundamental difficulty of debugging, how are you going to debug this? It's not immediately obvious how to debug this, because remember how this was generated. Generated from a deep neural network representation that has no idea what it's producing. It's producing from its ingestion of images, a composite image based on how fragments of images have been weighted and connected to each other by looking at a bunch of images. You can't look with your debugging system, you can't look at the code and say, oh yeah, unicorns don't normally have their horn penetrating the head of a man that's giving them a hug. You can't do that, and you'll see more about this as we go on. So this is just a list you can look at when you look at these things about what an analysis of that figure now a year ago was said to be wrong. And you can't generate this anymore. When I tried to generate it earlier on, when I still had access to Midjourney, it doesn't produce the same thing anymore. Someone has somehow changed how the synthetic output from that graphical large language model, where language includes images, has changed it and attempted to improvement. But as you'll see, that's not easy to do.
Hey, Randy, you're in the middle of the screen, and as a viewer on Zoom, I can hardly see it. It looked like a sausage roll with a stick through it, but I can't see it. Maybe you could move the camera to the left and get a better picture of the screen. Sorry,
The screen is broadcast with share.
Yeah.
Nothing to do with where the camera on the computer.
Share. Okay. Thank you.
Okay. Thanks. Bobby Joe sees what the most of the users online. So sorry if you couldn't see that. No, he isn't. Okay. So you're looking at something else when I don't know if that helps or not.
Yeah, it does.
Okay. So what I want to talk to you about now briefly is to lay out how there is a whole spectrum of these foundation models, not just the deep neural networks created by transformer algorithms, taking input, recognizing weighted relationships amongst components and building the deep neural representation. There are other ways of doing this. And what I want to try to do is give you a sense of what those other ways are, and maybe more importantly, how those other ways could be combined into the equivalent of a full stack model for foundation models. So that's what I want to do now. So here's the start of it. These are at least these four broad categories of what you might identify as the religious basis of foundation models. So many people think that there's only one, and that is the deep learning based foundation models. Try not to take them too seriously, because if there was only one, then they would have produced much more impressive performance than they have to date. We keep simplifying the problems so that they look like they're being more impressive than they are. Reinforcement learning based foundation models are interesting because that's seemed to have emerged as the first step in improving the deep learning based transformer foundation models. And most of the people here who are disciples of the Church of Reinforcement Learning will have coherent arguments about how reinforcement learning can help improve deep learning, and we see all kinds of evidence of that in the literature. But there are others, and two I want to connect are probability-based foundation models. That is just representing dependencies amongst random variables and being able to use Bayes' rule to propagate probabilities. So I can say, as you'll see in a second, I can say what the probability of an answer is. So I might give an answer that says, it's unlikely that the population of Pluto is 4 million. And finally, the ones that I have investigated most in my career, logic-based foundation models, are interesting because they provide the basis to determine whether an output is correct or not. So you can talk about what it means to have a process that is sound, that is guaranteed to produce output, and you can investigate when it produces conflicting output, you can investigate why. That's the thin edge of the wedge on explainability, which I will use to tie all of these three together. Let me say a little bit about them. This isn't my observation, but two people I spent some time talking to in Europe and in Canada have pointed out that the economic laureate, Dan Kahneman, who has passed on. By the way, he used to be a professor at the University of British Columbia and came to the AI seminars we had like this and in the old days. So I know him personally, but he's dead now, unfortunately. But what he left us with is some legacy. And this book about thinking fast, thinking slow is very closely related to this spectrum of foundation models in a way that I'll argue like this. So this diagram comes from someone, in this case, Luc Dereet from Catholic University in Belgium, who tries to think about that framework and what thinking fast and what thinking slow is. So thinking slow is actually reasoning logically and probabilistically. It's actually way more computationally intensive than simply grabbing the output from an LLM. However, the LLMs, despite what we hear in the popular press as being so expensive, are associated along this alignment and spectrum of thinking fast. So I'm going to get you a good answer really quickly, but I can't guarantee that it's accurate. We used to have this debate and analysis of computational complexity at the University of Waterloo, where I was an academic, and the University of Toronto, which was a bastion of computational complexity. And we kept telling them is if you don't care whether the answer is right, I can solve all your algorithmic problems in constant time. There you go. So here is a famous thing that is also pretty old. Jean-Paul Sartre from the 30s, a French philosopher. This thing in Sartre's, sorry, the 40s, published with this picture. And so what I want to do is motivate the idea about why thinking fast might be useful. So you come home one day, you look under the table in your dining room, and there's a tagger. How it got there, you don't know. What it's going to do, you don't know. But as we know about animals that are powerful and wild, it may be a risk to you. So you're going to get a fast answer from your transformer-based system. The fast answer is, get the hell out of the kitchen. Right? That's independent of whether that's actually a tagger under the table, which Sartre spoke about. It may be, how many people have dogs? We need more hands coming up about dogs. That's obviously not right. It may be a dog dressed up in a Halloween costume. It may be your best friend. But the point is that at one end of the spectrum, there is high value in quick answers, because if you get out of there and it was a tagger intending to eat you and it got out of the zoo and crawled in through your open window and was eating a chicken underneath your table, it might think that you're the next snack. So that's true. That's part of the motivation along that spectrum of thinking fast, thinking slow. If you were to reason about all of the possible explanations of how a tagger got under your table and whether it really was a tagger and not a dog in a Halloween costume, it might be too late. And that kind of reasoning takes a lot more effort and a lot more substance. So back to this model, you can think of this spectrum as towards the right. In this case, when I'm observing this, in this end of the spectrum, you can think of this as thinking fast and not thinking slow. That's one of the strategic hypotheses that comes not just from me. I subscribe to it, and with Luc Dereet, Frank van Harmelen, and a few others on the planet say there is a relationship between all of these foundation models. There's one aspect strategically of the relationship between them. That probably means if we're debugging something as complex as a large language model, we might need the development of contextual tools like your symbolic debugger for your Python program. We might need things further to the left on this. You might be willing to spend 5 extra hours debugging and proving the correctness of your algorithm rendered as a Python program. If it takes a lot more tedium, that's okay if you get it and it's correct. So that's another way to think about this. What's not at all clear, Vadim Belikko pointed this out to me, and in hindsight, it makes a lot of good sense. It's not clear whether these foundation models, whatever ones you pick, not clear that they should be debuggable. Let me give you an example of a famous Nobel laureate AI person, Jeff Hinton, whom I know quite well because we used to have arguments between Waterloo and Toronto the old days. He doesn't think they should be debuggable. What that amounts to is that the context you build around your program to debug it is unnecessary. You don't need to explain things. They will eventually be so smart that you wouldn't understand how they come to their conclusions, produce output anyway. So that's one position, is foundation models need not be debuggable. I don't take that tact. I take the opposite philosophical position, and it comes from being a computer scientist. Right? The first computer program I wrote did not work. What a surprise. Has anybody ever wrote a program that doesn't work? How come all your hands aren't going up? Those who don't put up their hands are likely never wrote a computer program, I guess. I don't know. Not intended to be critical. But that's a fundamental philosophical position that you have to decide you take. And if you think that foundation models don't need to be debuggable, and you don't care about whether the estimate of the people on Pluto is 4 million or not, or think about this, yesterday, Trump's executive order to rescind all of the AI orders from the previous administration to say, we want to concentrate on AI and make sure they're free of ideological bias. What he's really saying is free of other people's ideological bias, not mine, right? So be cautious about what you want to debug. So now this is a bit of an eye chart, but I'll explain each piece of it in components. So here are 3. Reinforcement learning isn't in here, but that's just to make the argument a little bit clearer. 3 different situations where you want to debug things. And in the first one, this one over here, this is based on belief revision, non-monotonic reasoning. This is based on Bayesian probability. And this is based on something that is very difficult to debug. So in this one, upon learning that penguins don't fly, the previous prediction of Tweety flying is rescinded. In this one, upon learning that Tweety is a penguin, the probability of Tweety flying becomes much less than 0.8. And in this one, the prediction that Tweety flies remains because we didn't debug the problem. We didn't debug the deep neural network well enough to reduce or prevent that consequence. This is not a surprise. And I'll give you just a brief oversight about why that's the case. Notice it's still on this spectrum of thinking fast and thinking slow. Back to the tagger under the table, it takes a whole lot more reasoning to consider all of the hypotheses or possible explanations for how a tagger could have got under your table in the first place, which may not be quick enough to prevent being eaten by the tagger. So this is just what I said about that. And I want to say a little bit more than just show you that is there's a whole field of so-called belief revision when your representation is precise enough to be assessed with respect to its meaning, to say, if I know A and I know A implies B, and I say, oh, you don't know B anymore, then we can choose to revise our theories and revise our beliefs, and we then might be forced to choose A implies B and A, that is, we get rid of something in the original knowledge base in the foundation model. That itself is fundamentally hard to do, to make that choice between those two. One of the ways, a former PhD student here said, to resolve this, what we do is we simply take beliefs and disbeliefs and we demote them to tentative beliefs, which is exactly what happens in probability. You reduce the probability of a belief. So won't say more about that. This one, reducing the probability to say the probability of Tweety flying now is much less than 8, requires, and now introduce something that there's some confusion about. I'll try to resolve that the way that I use this notion of loss function. You need guidance about the conclusions above to be able to change the conclusions below. So in this case, what we know from what we understand about probabilistic reasoning and Bayes' theorem is that the guidance is we have to adjust some of the priors to be able to reduce the probability of Tweety flying. And the prior we reduce is the probability that Tweety flies is greater than 8. Doesn't make any sense anymore. We can reason about that. It may take longer than just adjusting weights. So that's the second part. And this is a whirlwind tour through some aspects of debugging. That's the guy. Anybody remember when Thomas Bayes did this work? Before he died. Good answer. Logical answer, right? Yes. Yeah. So he was the Reverend Thomas Bayes, and he lived for, I think, 59 years from 1701 to 1760, something like that. So he was a non-professional mathematician that invented a common sense rule to propagate probability even before I was born. Now, I put this in here because in the reference to a loss function, if I took each of the graduate students and Amy into a room, separate room, one at a time, and asked them what a loss function was, if there were 300 students, I'd get 300 different answers. They wouldn't be all unrelated, but the way in which I use a loss function is in the one highlighted in red. So a loss function began by being a measure of the difference between an output classification and a neural network, and by the correct classification and the incorrect classification. So you want to measure that. If you measure that to be different, then that is a motivation for going and debugging the neural network. So you can adjust weights along those weights that you think were propagated, were used to propagate the classification. So I use loss function in the sense highlighted in red, and that is I'm looking for a measure that helps me understand that the output was incorrect as the threshold motivation to say, now I know I have to do debugging. And I want to do debugging across all of those models. Just a hint, for those of you who are part of the Explainable AI Lab, you already know what's coming, is that explanation is what you get from the context around debugging your programs, because what you hope you get is an explanation and say, oh God, in that loop, I forgot to increment a variable that's used as the test for the loop termination. Standard problem, right? So that's an explanation for why your program wasn't working in that regard. Now, here's a hint of what's coming, is that stacking these different foundation models together is based on the definition and fabric of explainability. Now you know it's no surprise that reinforcement learning provides a concept of explainability for the foundation models rendered by transformers giving deep neural networks. So that's why that is here. So in the statistical version of adjusting weights, in this case, like I showed in the other example, you're liable to not correct things. So you adjust some weights because you measure some difference in the output classification and what you expect. You go in somewhere, somehow adjust weights, and then you ask the question again. In this case, you get the same answer, and that's a frequent situation with those models. One of my students in a recent graduate class produced this example, which I won't go over in detail, but it's just an example that shows how backpropagation, measuring gradient descent through different epochs can produce the same output whether you adjust it or not. So that's the motivation for cascading these models together, is that the hypothesis, as you'll see in a second, is that debugging across that spectrum of foundation models is not only better, but necessary if you actually believe things should be debuggable. So one can be used to debug the next one and so on and so forth. How many people have heard of so-called reinforcement learning by human factors, RLHF, right? So that's a fancy label for getting humans to provide feedback without specifying which of the humans has the authority to say whether the outputs are correct or not. So in that cohort of humans looking at outputs from LLMs and voting, if you like, on which output is correct, you don't want to have Donald Trump on your team. Just saying. That doesn't mean it's not a useful way to think about things. So here's the framework. So I'm going to take this idea that I presented already in this spectrum, thinking slow, thinking fast. And here's what I'm going to do. I'm going to stack them up. And here's what I claim based on the experience I have of how you interrogate these models and use them, is you really only do three things with them. You query them, so you ask them questions. You update them, so they learn more, so you change the model. And you produce explanations. That's all you produce. So back to your program inside of the context of debugging. The debugging context is supposed to explain to you where your errors were in your program. And so what I claim is that you want to stack them up this way. And now what does that mean? Well, yep. Both, but this nomenclature I tend to associate with background that you have, which is database and data mining. Is update can mean updating driven by a threshold of error, or it can mean the one you just mentioned. I think both are relevant. But notice this doesn't say about reinforcement learning with human factors. That I think is a highly specific, not so informative opportunity. But what I want to leave you with before I get to the second elephant in the room is just the association with what I said right at the start about foundation models. So it's easy to label all of these things as having at least, and perhaps more, but at least two components, and I've labeled them this way. So we know with logic-based models, we want to capture facts and inference rules, and we want the system in which they're embedded to be able to help us explain and debug them, and that's typically using inference rules and facts. The same is true with dependencies that are recorded. This random variable of being a bird is connected somehow by some strength to this random variable of being a penguin. And we have those dependencies and priors, and we have Bayes' rule to make or draw inferences about what happens when things change. In this case, I've included reinforcement learning to say what you have. Well, you're trying to learn action policies. So what you want to do may be perpetually under revision, but you want always at any state transition in the world to make a prediction of what the best action is given the reward and return to be able to make that choice accurately. And in the last one, the deep learning models, you have weighted dependencies and encoders and decoders. Now, what I want to point out is that the coloring I have on these four is not accidental. It's not just for eye candy. Is that one of them tends to be the specification of how the other can be manipulated and debugged. So all the way back to the connection, and I can say this, is that every one of those models has this Gödel-Turing-Hawking structure. Self-representation, like the environment you use to debug your Python programs. That means here are now 4 opportunities to be careful and not get too close to the edge. So Gödel's theorem applies is if your light blue part gets too near the edge of what it represents, it can prove to be impossible to write that program and to execute it. So think about it that way. So here is the biggest takeaway from today's short talk. The first one is weak self-representation implies weak reasoning capabilities. It seems that every day or every second day, the quote AI experts in the world from Meta and OpenAI and Google in some sense, also Microsoft, are making claims about being able to improve those basic foundation models with weighted deep neural networks. Say, we can get them to reason. Well, they weren't designed to reason. How many people have children? Okay, well, get a dog or a child. I don't know which one you would find easier to look after. But the point is that if something isn't built to do something, how many people ice skate? Okay, now I want hands up from people that don't ice skate and never have any intention of ice skating. Good. Now think of yourself as a foundation model, and I'm going to fine tune you to be a professional hockey player. Do you think that's possible? No, not at all. It's exactly the same thing here, is that you can't fine tune something to do something else than what it was designed for. You can't fine tune my telephone to be an automobile. That's not what it's designed to do. So that's part of this. Hypothesis one is that the correlation between the power of reasoning and the power of the representation is explicit. The second thing, and this is a question about acronyms. There's a new one in here I should add, is artificial intelligence or artificial general intelligence or artificial superintelligence, excuse me, or one that Gary Marcus published last week is BSI. And he claims that, you know, I came from the prairies of Canada, so BS means something different for me than what it does for him. But BSI is basic shallow intelligence. Don't criticize basic shallow intelligence, because not being eaten by the tiger under the table is a good thing, right? You want to survive. So the second hypothesis is that any scientific formulation of AI needs a complete stack along that spectrum. And I'll show you, I've showed you a little bit of what it looks like. So for example, non-monotonic reasoning and the application of belief revision to find coherent models, such has been the study of many people, including Jia Yu and I, is fundamental to reasoning about change. It's not old-fashioned and should be dismissed because the last paper on the foundations might have been published in 1998. So keep that in mind. You need that, and it can help you inform you about changing probabilities and weights, and said, here are a set of beliefs that are consistent. Here is a competing set of beliefs. You decide which one to adjust the priors on. So we can do that. Model-based reinforcement learning policies. I have a student doing some work on this so-called distributed Q networks, can help accelerate the convergence towards identifying policies, but those policies can be used to help the thing at the end of the spectrum, the deep learning models, can help to debug those. Just so it doesn't seem like Randy is old and howling at the moon, he may be, by the way, right? I'm a scientist after all. Here's something that just came out, I think about 10 days ago. The interesting thing about this is that the fundamental AI research group at Meta said, we're doomed to try to debug deep neural network models. We need some kind of structure. So this is a paper that comes from them that shows 2 steps in building these layered models like the one I just showed you. So I'm not a complete lunatic, or maybe both of us are complete lunatics. So that's another one. So just to think about these scalable, they call them memory layers. And I've already showed you is that what's stored and recorded and learned at the logic, probability, reinforcement, and deep learning are all different layers that need to be stitched together with the notion of explainability. But notice what they said. We also want the inference speed of nimbler models. So if knowing that could be a tagger under the table gets generated in microseconds and saves you from being eaten, it's still useful. So keep that framework in mind. This is another one. So part of this comes from some discussions with Osmar and my colleague in medicine, Ross Mitchell, is previous work on visualization that I did myself always leads me to say, what does a deep model look like? How can I identify where to debug it? So when Llama 3 was released, seems to me not very long ago, but at least a year ago, it said two things that caught my attention. One is it uses this safe tensor format that you can read about. One is that it represents model weights in B float 16. That's just an easy representation in terms of bits. But I struggled to find a diagram. So I had this diagram to say, how can I visualize the complexity of multidimensional weighted space? So I started with that one, realized that it's not that simple. So I got another one, and this one comes from visualization from a place called Sphinx on tensor plots. So that gives you a fragment of a weighted network, and all of those things have weights according to what you can see in that diagram. Now, debugging, just like when you put your Python program in the context of finding variables that you didn't expect to have those values, debugging amounts to finding some sphere of influence. So that's the way to think about that. When you use this cascade of foundation models, you want one of them to help identify where to look in the next one to be able to say, oh yes, thank you for your help. Now I know if I focus in that sphere, there is where I could, for example, adjust weights to hope to produce differences and improvements on what comes out. Oh yeah, absolutely. And Osmar is a member of the Explainable AI Lab, as he just so deftly demonstrated, is that the connections between these things and how you explain how they're related is fundamental. I always tell the undergraduate students about debugging. I said, you know, one of the best things to do when you're debugging your program is to explain how you think your program works to somebody else. I've even seen examples of having a computer program explain to your dog or your stuffed animal. In articulating what you think your program is doing, you often reveal to yourself the kinds of bugs that emerge. They said, oh yeah, that doesn't make sense. And explanations that way are essential. About 7 months ago, to their credit, some subset of people at Meta and Google, I haven't seen this at Microsoft or OpenAI, it may never emerge, but some of them said, yes, we have to debug. The only way we're going to debug those kinds of foundation models is by being able to visualize, so give humans a spectrum of tools to look at how to isolate those. And so you can look at this model explorer from Google, which says we need to be able to look at the deep learned models and isolate where to look. And so they built this tool that you can use. It only works on their own, and it looks like this. Remember, I've studied the theory of visualization for quite a long time, and this is still ugly, but this is the evolution of that simple framework for debugging your Python program. I mean, so it's not just me that's saying we need these layers and we need to be able to inspect where things go wrong. Is apparently people at Google believe this too. So I could stop here, but I won't. But let me quickly go through another elephant in the room. There's this one too. And this is related to scalability. I've had quite a few discussions on some trips that I've made with Rich Sutton lately. A lot of people refer to, for example, his paper from 2019 called The Bitter Lesson, which says we should learn that some things are scalable and some things are not. And so I want to leave you with that before I conclude. They're that elephant again. So remember how old I am and the experience I have with AI. Just provide more input and more compute and the problem will be solved. That's what IBM said about chess. In fact, I worked for IBM as a consultant for 2 years in the 80s on the design of hardware for logic programming. And IBM managers essentially came back after a year of working with them and said, Randy, the design for the execution directly of logic programs is way too efficient. Could you make it a little less efficient so we can sell more machinery? They literally said that, right? Sam Altman says we just need more compute, right? He's an example of someone that that all of our graduate students should only pay attention to when you want to delve deeper to criticize that. Robo-taxis is another example. So I could diplomatically, benevolently say, admire the enthusiasm that people have. But in the case of Altman and Musk, it's got nothing to do with enthusiasm. It has to do with making more money. That's the bottom line. Here's my claim in the summary of the relationship to the bitter lesson, and this is taken from Rich's paper, is that what seems to be scalable is search and learning. So, for example, in IBM's case with chess, what was scalable is searching deeper to be able to be further ahead of you in anticipating your moves. So if there's 276,000 different moves you can make from this position, and I can search that far, I'm going to beat you. It's as simple as that, right? So does that scale, and does learning scale? Well, not clear how learning scales if you think of changing or debugging as learning. The basis for calibrating whether you're making improvements has become more and more important. And whether you take my advice about the hypothesis of logic, probability, reinforcement learning, and deep learning, whether you think that those should all be coupled together or not, it's still the case that we want to be able to determine how to compare, differentiate these systems. So, of course, OpenAI comes out almost daily with new claims about being able to do things. Francois Chollet, who now has his own company and has left Google, contrived the so-called ARC prize, which probably Matt knows more about than I do, is my guess. Because this is, but to what I know about, and having traveled with Matt as well, is that visual configurations of these kinds of things can be learned, right? I always remember your is it Flappy Birds? Yeah, Flappy Birds talk. So these can be learned, but they can be used as a test to see whether or not your foundation model knows what it's doing. And just the last thing about Marcus, you can look at these things. This case, Marcus, I pay attention to because he always has some very well explained, if controversial, reasons why things aren't working as claimed. But this paper from Apple says maybe there should be a different view of artificial general intelligence. And of course, many academic scientists remember, especially when you think about announcement this week for, I don't know, 500 billion, 1 trillion, 1.1 trillion investment in AI. It's got nothing to do with AI. It has to do with developers selling space and equipment like computers, which when running blow warm air on your feet. That's what that's about. But the academic scientists are the bastion of doing that. So here's the last thing. This came out just, I think it was Thursday, from Gary Marcus, which put this on the left. Influencers have gone wild claiming that AGI is imminent. And then Sam Altman tweeted, Twitter hype is out of control again. So this is the first time in my observation of paying critical attention to both of these people, says, we're not going to have AGI next month, nor have we built it. We have cool stuff, but reduce your expectations 100 times. Now, maybe today he's going to change it because he was part of this discussion of that $1 trillion investment. So that's the whole story. Be cautious. And here are the summary and the takeaways. You will have to blend those foundational models. If you think you're going to achieve artificial intelligence, remember, I come from a generation where I don't buy into artificial general intelligence and artificial super intelligence and BS intelligence. Maybe the last one a little more. But if you're going to pursue a scientific theory of intelligence, you won't be able to do it without blending that spectrum of models. And there's lots of growing evidence that that's the case. And the blending might not be uniform. So we see that in my work with Ross Mitchell in medicine. We see that there are different ways of producing explanations for the kinds of inferences that the AI tools we develop. There are two people, Nafisa and Jai, have worked on projects where explanation comes out differently depending on the context. So it doesn't mean they're uniform in the blending of those things. It just means that they're necessary to stitch things together. You can't overestimate. So Osmar's been commenting to say something about the value of explanation. The choice of representation influences how we can explain things. And who are explanations for? They're for us, humans, right? As we're the ones that have to decide on placing trust in these systems. So we're the ones that get to evaluate explanations. Just that bit about loss functions have to be based on explanatory foundations. And the bottom line is no one foundation model is adequate. The last thing is a reference to a paper that I just found last week. And it's like the model viewing one from Google or the multi-layered one from Meta. It's a paper that says, here's how you can do model editing. And so the start there is to target the most basic level foundational models, the deep neural networks, and say, here's a tool that will help you debug them. So view those as your computer program, and that tool as the environment in which to do that. So that's it. 2 takeaways. One of the elephants in the room is that those fundamental principles and properties from mathematics, including Turing and Gödel, with Hawking demonstrating it, those are important for debugging. You have to be able to understand where the boundary is to not go too close to the edge. The second one is in this cascade of models, you want to be able to say, I need a quick answer. It's more important that I get a quick answer than a right answer. And at the other end of the spectrum, it's more important that I get a right answer than a quick answer. So that's the second part. Stitching that all together is explainability, like RLHF does for some deep neural network representations. That's it.